Hello, everyone, and welcome to phyloseminar.org. This is the second talk in a series of 3 talks on the Markov genealogy process. Please use the YouTube live comment box to ask questions. Today's speaker is again Aaron King. This is a continuation of the previous talk, so I'll skip introducing Aaron again and just say welcome and thank you for participating.
Thanks very much, Eric. Thanks again for the invitation to talk. So as Eric was saying, this is the second in a series of talks. Before I launch into it, let's see, is there? Yeah, I guess that's fine. So before I launch into it, these are some folks that deserve thanks, a couple of collaborators and people that have been good enough to talk with me about the issues that are involved here from the top to the bottom, as well as some people that have been foolish enough to give me money. The central problem that I'm talking about in this couple of lectures is this business of how can we learn about the structure and parameterization of the kinds of stochastic models that we want to use to explain epidemics and disease outbreaks from genomic sequences. Of course, we have data from other sources, and we're going to see that the methods that I'm going to talk about today allow us to incorporate other kinds of data. But the thorny problem is figuring out what genome sequences have to say. And as I was saying last time, the pathway that I'm constructing for this lies through a tree-like structure called a genealogy. This is not the only way that the information that genome sequences can inform stochastic models, but it is the way that I'm talking about today. And so the problem factorizes into two pieces. Both of them consist of constructing a predictive model. So given a genealogy, of course, we can ask, what does that genealogy predict about genome sequences that lie along it? This is a well-studied problem. And a much less well-studied problem, though, is how do we generate genealogies from stochastic transmission models and do that in a way that allows us to solve the inverse problem? So from a mathematical point of view, this is the problem. And this is a repeat slide from last time, but just to call this into our minds, we have some data in the forms of a set of genome sequences and perhaps some other time series data. We have these various components, a genealogical tree, which describes the pattern of shared ancestry among the sequences, a model of evolution of sequences, so nucleotide or amino acid substitution model, E, as well as this model that we want to focus our attention on, the dynamic stochastic model of the epidemic process. And so if you write the likelihood function as it's a function of the two components of the model, that's just the probability density of the two kinds of data given the model. And we can factorize that problem like this, or at any rate, that's what I'm doing, is factorizing the problem like this. And if this density of the sequences given the genealogy and the substitution model is called the phylogenetic likelihood, something that Felsenstein has written quite a lot about and done the foundational work on, then we might as well call this thing in red here the probability density of the genealogy, as well as perhaps other time series data given the stochastic transmission model. We might call that the phylodynamic likelihood. So I'm going to focus my attention on this red thing here. Okay, so what I'm going to show you is that any given population process, any given stochastic transmission model induces a unique genealogy process, a unique Markov process in the space of genealogies, that when we project that down onto the space of observable data through a process of pruning and obscuration, that there's a projection that consists of pruning and obscuring the genealogies that projects it onto the space of observed data, and that we can calculate or compute the exact likelihood for a given model and a given genealogy by solving a particular filtering problem. So I'll explain all of that. So the full details are available in an archive preprint. References at the back of the slides here. And a more high-level overview is given in the earlier talk. But this talk, I want to really focus on the mathematics of this and try to explain to you how we go about, especially this last step here. Oops. All right. So population process. What do I have in mind here? Essentially, we've got lots of different kinds of models that crop up in epidemiology, and they represent, their variations represent the hypotheses that we have about the nature of the dynamical system that is the dynamical epidemiological system. And so these are just some diagrams. I talked about this before, but just here, I'm just trying to give you a sense that there's a wide array of different kinds of models that we'd like to be able to entertain in our statistical inference. And we're interested in the parameterization of these models and in the comparison between the explanatory power of different models. So we'll focus on this one very simple one here, just so we can have an example. This is the classic SEIR compartmental model. And of course, we often write down a set of differential equations. This should be fairly familiar to most of us that go along with this. But we want to think about this as a stochastic process, and a stochastic process that has 5 different kinds, in this case, 5 different kinds of state transitions. So if we're at some particular state in the of the system, which is characterized by 4 different numbers, then there are 5 different ways that that state might change. And here, for example, we have transmission. We might have disease progression, where an individual moves from the E box to the I box, a recovery, a waning of immunity, or perhaps a sample is taken, which doesn't result in a change in the state. Each of these different state transitions I've labeled with a word, and I've collected the set of all possible state transitions into this set U here. When we think about this as a stochastic process, perhaps the most compact way of summarizing it in a single equation is to write down the so-called Kolmogorov forward equation, which basically describes how the probability of finding the system in any particular state evolves through time. So W here represents the probability of finding the system at time t in the particular state S given by SEIR. And we can see that there's one term for each of the 5 possible transitions, one of which represents the inflow of probability into that state due to that transition, and the other the outflow of probability from that state to another state when a transmission occurs. Well, when that event occurs. So transmission is the first line, progression the second line, recovery, and waning of immunity. And we notice that the state, when a sample is taken, the state doesn't change, at least in this particular formulation. So the 2 terms that would correspond to the sampling cancel out. Okay, so that's just an example. What I want to do now is develop the mathematical formalism so we can understand the basic results. And so we're going to posit here that this population process, this stochastic transmission model that we're so interested in, is some kind of a Markov jump process. So it needs to be non-explosive, which means that they're in any given finite interval of time, there are at most a finite number of events that occur, jumps that occur. But the space X can really be very, very broad. I can tell you the details about that later if you're interested. And this jump process is characterized by 2 different elements. One, of course, is the probability distribution of finding the system in any given state at time 0. So that's this P0 distribution. The probability of finding the system at time 0 in any particular set is just given by the integral of P0 over that set. The other thing that you need in order to characterize this jump process is a set of jump rates. So what is the hazard of jumping from state X to state X prime at time t? Well, that's alpha here. And here I've broken it out by by the various jump types, the set U, which is the set we looked at here. Okay, so in general, set U will have to be some countable set. These alphas can be quite general. They need to be positive. They need to be it needs to be non-explosive, so they have to be finite when we sum them all up. But there are no restrictions essentially placed on what kinds of events are allowed. So this is a very general jump from one state to another state. We can have, for example, multiple infections that occur simultaneously. sampling events that are complex. All kinds of complexity is possible here. And this flexibility is important because the goal overall is to facilitate the consideration of scientifically interesting models. We'd like, as much as possible, to have the statistical methodology not stand in the way of our ability to draw the conclusions that we're interested in, to ask the questions we want to ask. All right. So in this general context, this is what the Kolmogorov forward equation looks like. It's basically just a sum of these two terms, sum over all the u's and all the x's. Again, if we sum up the w over some set e, we get the probability of finding the system in that set. All right. So I've told you what kind of population processes we want to look at. Now we need to think about what a genealogy is. Again, this is a little bit review from last time, but we think about genealogies as having this tree-like structure. But of course, if we think about it, at every point along each one of these lineages, that lineage of virus or whatever it is was present in one of these demes, in one of these boxes, right? And so in fact, it was either in this very simple model, either in the E deme or in the I deme, because the individuals that are recovered and the individuals that are susceptible are not infected, so they don't contain any of the virus by assumption. So what that means is that we can color, if you like, the branches of this genealogy, of this tree, with the color blue or yellow, depending on whether the lineage was in the E deme or the I deme at that point in time. Now, this exists conceptually. Of course, we can't see this, and that's one of the fundamental problems we have to overcome in order to do effective inference. But this, if we can posit that model as being a description of the way the system worked, then we're not making any additional assumptions by assuming that that this was really happening, right? That there really were some colors there that we just are not able to see. So we'll call the set of demes. Every model will have a set of demes. It'll again be a countable set. That's a restriction of the theory. Here, this blackboard bold D is the set of demes, and here we just label them E and I. All right, so it's in order to understand how a population process induces a genealogy, we need to figure out how each of the possible kinds of changes that can happen in the state of the population process, what changes they have on the genealogy. And it turns out, kind of importantly, that all of those changes can be viewed strictly locally on the genealogy. So if we focus, we can always focus on a particular narrow interval of time, infinitesimally wide interval of time at this genealogy, and ask, well, what does the event that occurs in the population process in that interval, what does it do to the genealogy? So it does one of 5 things. Every event that occurs in the population process does at least one of 5 things. And so the sort of elementary possibilities are that a birth event occurs. So for example, if there was a transmission event, that corresponds to a birth event here, where, for example, an infectious individual gives rise to a new latently infected individual and otherwise carries on. It can also, an event in the population process can lead to a death type event, for example, a recovery, which means that this lineage here of an individual that was infected is now recovered. So that terminates that lineage at that time. And we actually lose the ability to see the last part of that lineage. So this dashed line reflects the sort of loss of that lineage, from dropping of that lineage from the genealogy as a result of that death event. We can also have migration type events. For example, when a latently infected individual becomes productively infected, that's a movement of a lineage from one deme to another. We can also have sample type events. So here's an infectious individual who's sampled. I'll use a blue dot here to represent the sample. Of course, some events, like the loss of immunity events, don't have any effect on the lineages. And so those are of neutral type. And then we can cobble together these 5 basic types essentially in an arbitrary fashion to form compound type events. So, for example, in the classical Moran process that forms the basis of Kingman's coalescent, we have these events where a birth event occurs simultaneously with a death event. In here, the situation, we have an individual that's sampled and then for whatever reason, maybe quarantined, they become, they're removed from the infectious pool. Here's a compound event where we have a migration event simultaneously with the birth event. But we can put these things together in various ways. And the point is that for any given model, there is some set of events. And if we know the model, we know what these events are. Eric, did you have a question?
Yeah, I was just curious, you mentioned loss of immunity for the neutral.
Yeah.
So is there something more, can you say a little bit more about that? Is there,
Well, so in this model, right, when an individual loses immunity, that corresponds to somebody who's in this immune compartment transiting over here to the susceptible compartment.
But
right?
How is that not a Deem transition?
Well, because this individual doesn't have any virus in them. And so there's no impact on the viral lineages. There's no impact. So the genealogy is tracking the viral lineages that are ancestral to the genomic samples that we've taken. Maybe I should have said that at the outset.
No, I mean that's making sense. My mind is a little bit in knots now. So the states are the states are on the viruses. But it's the virus. It's like it's the person containing the viruses.
Yeah. So I mean, it's not necessary to make that assumption for the theory to work, but there has to be some connection between the viral lineages or whatever it is, the pathogen lineages that we're following, and the state of the population. So in these compartmental models, like we have here, that's probably the prime use case, right? So the prime use case would be where we're modeling the hosts here using this epidemiological compartmental formalism, but some of the hosts contain viruses, and it's those relationships amongst those viruses that we're hoping will give us information about the overall dynamics. So, for example, I've shaded in the compartments that consist of hosts that have viral lineages inside of them.
Yeah.
But, so, I mean, that is the most common use case and probably the one that is motivating most of the work here. But, we can certainly visit on the question of just how general this thing can be. I think it can be generalized quite a bit beyond that. But that's probably the most concrete example to keep in your mind.
That's great. Thank you. Yeah, I appreciate that. Thanks.
Sure. Okay, so all of this is to say that if you just simply follow the population process, the events that occur in the population process, and at every event make the appropriate change to the genealogy, you end up with a stochastic process on the space of genealogies. And last time we looked at some movies that showed this, that showed simulations, and we won't go back to those. Those are still available at these URLs. Couple of things to keep in mind: that the mapping from the population process to the genealogy process is a random mapping. And so there is more randomness in the genealogy due to the fact that it's which individuals actually participate in the population event that is random. And that's a randomness that's not present in the population process. And with respect to that, the key assumption that makes everything possible here is that the lineages within any given Deem are exchangeable. So they're not necessarily independent of one another, but they have the same probability distribution. Every individual is as likely to participate in an event as any other individual in that Deem. And this assumption is technically an additional assumption, but I just want to point out that when we've actually posited a compartmental model, essentially we've adding this assumption adds really very little more than that, right? It's usually implicit in our thinking in the very act of writing down that model that this assumption kind of comes along. So this is certainly very much in the spirit. It's not a restrictive assumption. Okay, so I've told you how a genealogy is induced, and we can think about that thing as being a kind of full genealogy, meaning it relates not only the samples, but also the extant individuals. So these black dots represent all of the individuals in all the lineages in the population that are extant at time 10. And we can see they have relationships to one another, and it also includes the samples, the blue dots. But if we project, we can't see these extant individuals. The only thing we have in data are samples. And so the first thing we can do is to prune the genealogy to get rid of the things we can't see. So now this is what I call the prune genealogy. We've just trimmed away those terminal twigs that between the black dots and the most recent blue dot. And that results in a prune genealogy. But of course, this we can't see either. As I was saying before, the colors here, which represent the location of each lineage within the scheme of demes, is not visible to us. And so if we eliminate that information, we're left with the obscured genealogy. But I guess I'll talk more about that in a minute. So we have to say a little bit about the relationship between the full genealogy and the prune genealogy. And again, we can do that by focusing on the local structure. So in the top set of rows here, I'm looking again at a narrow slice around a single event that occurs in the process. And we've got birth type event, migration type event, sample type event. And then the second row shows one possible prune genealogy that corresponds. So the act of pruning results in the dropping of some lineages. So here we have a birth event. If we prune it, then we lose some of these lineages. I've indicated the ones that are lost with dashed lines. We lose them because these lineages are not ancestral to any sample that happens in the future. So they get dropped, and we see that we end up with something that looks a bit different here. Here's a migration event with some pruning that occurs. Here's a sample event where we have some pruning, right? So some of these lineages get lost. And the idea is that which ones get lost is a feature of the data, but we need to focus attention on this in order to be able to characterize what's going on here. So there's going to be four quantities that become important, and I'll just briefly explain. Two of them relate to the top row. So the first is the so-called deme occupancy. So we just count up the number of lineages in each deme just immediately to the right of the event. So here we've got 1, 2, 3, 4 blues and 4 yellows. So the deme occupancy is the vector 4, 4. Here we've got 1, 2, 3 blues and 5 yellows. So the deme occupancy is 3, 5, and so on. The production of an event is the number of lineages that emerge from that event. So most of the lineages in this picture here are not involved in the event, but there are two lineages, namely this one and this one, that do emerge from this event. And one of them is blue and one of them is yellow. So the production of this event is 1, 1. Here's a migration type event where a yellow becomes a blue. The production is 1 blue and 0 yellow. So it's the number of lineages in each deme that are found immediately to the right of an event and descendant from that event. Here's a sample type event where two lineages are simultaneously sampled. They're both yellow, so we have a production of 0, 2. Okay, so two of the four quantities, the deme occupancy and the production. The second two are the lineage count, and they relate, and the saturation, and they relate to the bottom row here. So when we count up the number of unpruned lineages in deme I at time t, we get the lineage count. So that's the number that we actually would see in the genealogy. So 1, 2 yellow and 2 blue. So that's a 2, 2. Here we have 2 blue and 2 yellow. Again, 2 blue and 2 yellow here. So the lineage count in all of these cases is 2 blue, 2 yellow. The saturation is the number of unpruned lineages descending from the event, right? So just looking at the lineages that emerge out of this, in this case, we have 1 blue and 0 yellow. So a saturation of 1, 0. In this case, we have 1 blue and 0 yellow. And in this case, we have 1 yellow, and that's all. So the saturation is 0, 1 in this case. So those 4 quantities we can use to they're going to be the key features of the genealogy that enter the likelihood. Obviously, the saturation has to be less than the production, and it also has to be less than the lineage count, and both of those things have to be less than the occupancy. Did you have a question, Eric?
I was just thinking, like, yeah, let's just flash through. Okay, the saturation. Can you just flash through them again? The saturation.
Okay, so here's the occupancy. It's just the number, just to the right. Everything is just to the right.
Yeah.
Okay. The lineage count, or sorry, the production would be the number that emerge out of this event. So in the unobserved, the real thing. This is the full genealogy that actually we're imagining actually occurred. This is what the lower column is what we might actually have a chance of seeing, right? Because we've sampled. So the lineage count is the corresponding thing in the prune genealogy, and the saturation is the thing that corresponds to the production in the prune genealogy. So just the number that come out of this. So the idea is, given the model, we know the production for every type of event. And then in any full genealogy, we have the occupancy and the lineage, and sorry, the occupancy and the production. But when we've pruned it down, we have some portion of the production is the saturation. Some portion of the occupancy is represented in the lineage count. Okay, so now this is an important mathematical technicality. I'll just mention it. Is that this is a key aspect of the formalization that makes the theorems work. Is that we can view a prune genealogy as an ordered triple consisting of a time, which is the depth, which in this case would be 10, the total, the time at which the genealogy holds. A z function here, which is a function of time that gives the local topological structure at every point in time, and a coloring y, which gives us the sort of distribution or which lineages are in which colors at each time. So representing those things as functions of time is a key ingredient. Now, of course, ultimately we're going to have to project also onto. We're going to throw away the color, in which case, and that gives us, I'm calling the obscured genealogy, and that's just the t and the z components without the y component. Okay. Finally, we're going to see that certain combinatoric quantities involving those 4 numbers, the occupancy, the lineage count, the production, and the saturation, certain quantities come up again and again, combinatoric quantities. And so I'm just collecting them into this convenient notation here. This is not a matrix, but rather a number, a single integer, a fraction of it's a rational number, which is itself the product over all the demes of a ratio of binomial coefficients. So in the numerator, we've got the occupancy minus the lineage count. Choose the production minus the saturation, and in the denominator, the what is it called? The occupancy, choose the production. And this holds as long as this formula is valid, as long as we have these order relations that I mentioned before, and we just take it to be 0 if these things are violated. This is a fraction, and it's a number between 0 and 1, and it satisfies this identity. All right.
But surely there's some, like, you have some probabilistic interpretation of this thing.
Yes,
right?
and we'll see it crop up in the proof. Yeah,
Okay,
but I just wanted to define the thing.
Perfect.
Okay, so let's do the first theorem. Basically, the first theorem is going to be the likelihood of a given prune genealogy conditional on the whole history of the population process. So, here's a genealogy. It's got all of these branches, but it's also got these dots here, which represent events that occur along the genealogy, right? Some of them, the blue ones are samples. The green ones represent either migration events or branching events. And if we collectively just take each of those events, and here we've just drawn a vertical line through every dot, these moments in time here, where these represented by where the gray vertical lines intersect the horizontal axis, those we'll call the set of events associated with this prune genealogy P. Okay, so those are the events of the genealogy. Okay, so here's the statement of a theorem. Suppose we've got a given prune genealogy, and we're going to define this phi quantity here to be our binomial ratio that I defined just a moment ago, times an indicator function, which we don't need to worry about now. It's just a basic compatibility function. The key thing is that given the structure of the model, we can write this down once and for all. There's no dependence on anything. This is all well known. This is perfectly determined by the structure of the model. Okay, the theorem says that if H is the whole history of the population process, all of the events that occurred in the history of the population process, then conditional on that history, the probability that the prune genealogy is what we saw it to be is the product over all the events in the genealogy of this phi function. Product of all of just these binomial ratios, as long as there's compatibility condition holds. Here's an additional compatibility condition that the events of the prune genealogy have to be events of the history, right? If there was an event in the genealogy and nothing occurred at that time, well, it couldn't be there, and so it would be incompatible. This thing is just the indicator function, right? So this is 1 if this condition holds and 0 if it doesn't. And here I'm using this tilde notation as a convenient way of talking about the left limit, the limit as we approach from the left. Okay, so the proof of this theorem is, I want to sketch it out just so you have a feeling of how this works. So basically we want to compute the probability of this genealogy, and what we're going to do is, so this genealogy evolves through time. This is a snapshot at time 10 of a prune genealogy, but it evolves through time. So in particular,
I'm sorry to interrupt one more time, but like, can you just go back to the statement? So I just want to make sure. So that on the left-hand side of the conditioning bar, on the probability, that is our genealogy, and then H is the history.
The history of the population process. So in the paper, that's carefully defined. We don't need to go into great detail, but just think of that. We know we're conditioning on the entire sequence of events that occurred over the entire history of that genealogy. Okay, this is not a very useful theorem in and of itself, but it's needed to prove the theorems that are useful.
I'm just trying to understand, like, how do we have this history in hand, but we don't have the genealogy in hand?
Well, no, we have a genealogy in hand. We want to know what's the probability that we got that genealogy.
Right, but I'm just naively, it feels like if we were conditioning on this H, then we would know.
Remember, I told you that there's additional randomness in the map from the population process to the genealogy process. So the history of the population does not include all of the history of the genealogy. Right? Okay. There's additional stuff because it's the identity of which actual individuals were involved in those events that's still random.
This is this exchangeability thing. Okay.
Yes.
Thanks. Yes. Perfect. Thank you.
Okay. Yes, absolutely. That was a very good question. Okay, so basically we can think of this prune genealogy as evolving through time, right? And then we saw films of this last time. So here's what we might have after the 8th sample. So I'm calling that P at the 8th sample here. So if you count them up, we have 1, 2, 3, 4, 5, 6, 7, 8 samples. When the 9th sample arrives, that's this one, it adds a whole branch. In this case, it adds a completely new tree to the forest, right, to the genealogy, right? So something that is unrelated. In this particular instance, it goes all the way back to the root time. We can, when we go on to the 10th sample, that's this one, it goes back and it somehow manages to avoid coalescing with any of these other ones, and it goes back until it joins back up over here. Oh, no, sorry, it joins up, it goes back until it joins up here, right, which is this point here. All right, so the key observation is that viewed as a stochastic process on the space of genealogies, the prune genealogy process is a Markov chain. right? We can factorize the total probability into the probability of each of these transitions, from transition from this to that, the transition from that to that. And that in turn is basically a calculation of proceeding, where we can proceed backward through all of the events. Remember, we're conditioning on all the population events, through all of the events that occur, and compute the probability that what we saw happened. When we do that, we end up, if we fix one particular event, we can and follow what happens at that event as we move past it with each successive sample. We end up with something like this. So at the beginning, we have when the sample is first taken, the lineage count must be 0 and the saturation must be 0. But as successive lineages pass this, as we move forward in this Markovian argument, we either increase the lineage count by 1, or we increase the lineage count by 1 and the saturation by 1. And so at each point, we move either to the right or down and to the right through a diagram like this, where the probability of doing so along each branch can be computed from a knowledge of the production and the occupancy. And so one proceeds along this pathway, along whatever pathway actually happens, until you finally end up with what you have in the ultimate pruned phylogeny, pruned genealogy that you're looking at. And it turns out that whichever pathway you take, it doesn't matter which pathway you take, you always end up with the same product of probabilities, regardless of which pathway you end up. So it only depends upon the L and the S, the N and the R. And in fact, if you compute that, that gives you exactly the binomial ratio. You can also do this in one go, so that's that argument, very telegraphically explained, but very, very clear if you think it through. You can also come up with a more heuristic argument regarding just sampling without replacement, and end up with the same expression. Oops. So, I need to not do that. Okay. So that gives you just a sketch of the proof of this key theorem. That's where the combinatorics come in. That's where the binomial ratio arises. All right. But of course, that was conditional upon the history of the full genealogy. Now we need to sort of marginalize out that history. We need to integrate over all possible histories in order to be able to come up with the thing we want, which is the likelihood of the pruned genealogy, unconditional on the history. And so what we're going to use for this is a formalism that I haven't seen elsewhere before, but I've developed it a little bit for this purpose. And it's the idea of a filter equation. It's a pretty simple idea. So if we've got a continuous time Markov process with a Kolmogorov forward equation that looks like this, so this is the same kind of thing that I showed you before. I'm not telling you what beta is, but it could be anything. And we have, in addition, some function which we want to apply, some function b, which will be applied at every event. And that function can depend upon the event time. It can depend upon the nature of the event as well. And we're interested in computing the expectation of something which, conditional in the history, is just the product of this set of b's across the whole thing. Then it turns out that that is equivalent to solving another equation. So in particular, in particular, it amounts to solving equations of this form. So at every t which is not an event, then we solve this continuous equation. And then for every t in this set S, we have a singular portion. So there's a product, just an update that occurs instantaneously according to this. So this may be fairly mystifying to you. I've replaced one complicated expression with something that looks at least as complicated, But the key, the thing that we're going to see is that there's an immediate interpretation of these filter equations in terms of stochastic simulations.
You mind just clicking back one slide? So let's see. So okay, so this SDE is, or this forward equation,
Yeah,
is giving us the forward evolution of.
so we've got some random process, which is a jump process. So events are occurring randomly in time, and the state of the system is changing randomly in time. That's what this is telling you. At each one of those events, we have a number that's associated with that. And we're interested in what's the product, the expected value of the product of all those numbers. Okay, that's not surprising because that's the kind of thing we've got here, is a product of a bunch of numbers. Each one is associated with an event in this history. So what we want to do is figure out how can we compute the expected value of this, how can we across all histories, and what we get is that doing that is equivalent to considering this kind of a random process. So this looks just like a Kolmogorov forward equation, with the exception of the fact that there's this b, this boosting number here, which is basically a number which gets multiplied, at every event. So you're accumulating the product of these b's as we move randomly through time.
Yeah, it feels like some sort of reward.
Yeah, it's like you can think about it like that. If you think about this as in the context of what's that formalism called? It's basically Markov. Is it called Markov reward processes?
Yeah.
It's similar to that. Okay, so the theorem to state it uses these filter equations. It basically says that we've got our prune genealogy, and W now satisfies the initial condition of the original process, and this filter equation where the boosting, this B role, is played by the Ph's. Then by summing up all the W's at the end, we end up with the likelihood. So this shows us how mathematically how we can integrate out all the history and end up with just the likelihood of the prune genealogy. Okay, and this uses the coloring of the prune genealogy here. So again, here Y represents the coloring, and YT is the coloring just to the left of the point T. And so it uses those things because these are needed to compute those binomial ratios. So, but we still, of course, don't see the coloring. And so we need another theorem which tells us how to compute the likelihood of an obscure genealogy. So, but at this point, we can already solve simple problems. Like if we only have one deme, then there's only one color. And so that aspect of it is trivial. Just to show you, this is the filter equation that corresponds to that theorem. It looks just like the Kolmogorov forward equation, but there's some additional terms that crop up in a few places. This is the singular portion. This is the singular portion. So this holds at the events that occur, whether they are branch events or internal samples or terminal samples. We have this product here. So all of this general theory here gets specialized once we've picked the model. Gets specialized. So in this particular case, this is what that filter equation looks like, and we can easily solve that because this is the Kolmogorov forward equation. This filter equation is the Kolmogorov forward equation for a certain kind of reward process. So we can calculate that expectation, which is the likelihood in this case. And here, this is just a simple example. I showed this before, but we've got some data. We've got a tree, a genealogy, which corresponds to this SIRS model. And here we're varying one of the parameters and just computing the likelihood. We can see that we have a strong curvature here saying that there is information in the data about the value of this loss of immunity parameter. And we see these little error bars, which represent the Monte Carlo variability associated with this particular way of computing the filter equation. Okay, but as I say, we need to solve a much more, somewhat more complex problem in order to have this really be useful in the general case. So we don't have the colors Instead, we have an obscure genealogy, and we want to know how can we compute the likelihood of this. So the trick is going to be to proceed as we did in the previous case from left to right, from earlier times to later, but we're going to color the tree as we go rather than we'll start out with an obscure tree, but we'll gradually color it in from left to right in a random fashion. And the precise way we do that is up to us. We can choose the way we choose to paint the tree. And so this is essentially an importance sampling trick. It's very general. It says that we choose any kernels pi and q. So these are probability kernels. This is the probability that the paint, given that the system is at time t in state x and transitioning to state x prime, and that its color at that point is y, what's the probability that it changes to color y prime at that point? It's a probability, so it's got to be non-negative. It's got to sum to 1 across all possible colors that are compatible with the tree. And we need to have the property that there is some probability of making a color shift if there is some possibility if that could happen in the model. Similarly, the Q represents the probability of the colorings at the root time, and those have to be compatible with the model as well. So essentially, we have full freedom to choose these importance sampling kernels as long as they satisfy certain minimal compatibility conditions. And as long as we have that, then we can compute the likelihood of the obscure genealogy. So we have an obscure genealogy. The colors are gone. We don't have them. I say there are probability kernels. In fact, there are many probability kernels. The question is not going to be finding one. The problem is going to be finding a good one. But basically, one modifies the transition rates by multiplying by the one probability kernel and compensates for that by dividing the boost by the same probability kernel, so that the term that appears in the filter equation is the product of those two things, so the kernels cancel out. This is just importance sampling. And similarly in the singular portion. So the proof is actually fairly straightforward. It's a little bit finicky technically, but basically it's just the cheap trick of importance sampling that allows this to work. Right, so in the end, by summing up over not only all the states of the system, but also over all the possible colorings, one obtains the likelihood. All right. So again, this is these filter equations. This is just another set of filter equations. These filter equations correspond to, for any choice of these kernels, pi and q, it corresponds to a stochastic process that you can simulate. And if you do that, you can compute the likelihood. So I want to point out there's always a naive choice of these importance sampling kernels. In other words, the one that is sort of like most obvious just from the model process itself. So here in the SEIRS example, so this is a non-trivial example with 2 demes and some data, a small genealogy here. We can do the same kind of game that we did in the earlier example, and here varying a particular parameter and computing the likelihood as we go. So the variability in the likelihood evaluation, again, is due to Monte Carlo variability in the solution of the filtering equation. But we can already see in this small problem that variance is non-trivial. So we're starting to see more variability here. And that's reflective of the fact that we've just done the most naive choice of these importance sampling kernels. All right. So the challenge is,
can we just walk through, like, there's so much. I feel like I'm poised, like we're.
Yeah. You're almost there.
But it's like, so can you just, like, from a practical standpoint, so can you just walk us through
what this simulation actually looks like?
Yeah. So we take a simulation, we calculate some important weights.
Right. So first we choose how the coloring is gonna look, right? So the naive choice, you would say, okay, if there's a transmission event, then in this SEIR model, right, a transmission event means that we have somebody is born into the E deme with a parent in the I deme. So that means we pick one of the yellow lineages because we've painted it up to this point in time, right? So we've got a yellow lineage, and we pick one randomly and we give it an offspring and call it blue. Okay, there's actually two ways that, right? Either A is blue and B is yellow, or vice versa, right? So you have to think about that. If it's a recovery event, then we pick one of the yellow and we terminate it. Actually, that's a bad example because we wouldn't actually do that. But maybe a migration event, we pick one of the blues and turn it to yellow.
But I get the idea. So we're sort of
Right.
like realizing the potential trajectory.
Right. And so that choice of those particular things that I just described, that corresponds to a particular form for this pi kernel here, right? Certain changes of coloring occur. That's what the pi is all about. And the condition is that if it's possible for it to occur, it's got to be possible for that to happen. Otherwise, you're going to miss the portion of it, right? Okay, but there's nothing that says it has to be a good choice, right? It just has to be non-zero. So it's a very weak conditions needed for this theorem. So if we look at these filter equations, what they say is basically you simulate this process. So this is the augmented process where you've got the population process evolving. You also have this coloring process evolving. And at each event, you track this, you multiply the appropriate number, which is given by this. And you just do that through the whole thing. And then at the end, the number you get is the likelihood associated with that particular realization. So if you average that over many, many realizations, you get the expected value. Now, of course, that's a very crude way of doing it. And there are more clever ways of doing that calculation that involve sequential Monte Carlo instead of just sort of brute force simulation. But all of that's been pretty well studied, and we can talk more about that.
It feels to me like you have like your observables, you have some latent state. You use some procedure by which you calculate the latent state. The latent state allows you to evaluate the full likelihood, and then we take an expectation over realizations.
Exactly. Okay. Exactly. That's exactly what we're doing. So this is, I mean, from the point of view, this is just a partially observed Markov process model, right? We've got a latent state. Here, the latent state has been augmented to include not just the state of the population process, the model that we started with, but also this coloring.
Great. Thanks. I'm sorry it takes a couple of times for me to get it.
No. I really appreciate it because, there's a whole lot here. And, I don't imagine that this is obvious to anybody. But if you unpack it, right, but that's what we're doing. That's the whole point of the talk.
Great. Thanks.
Okay. So what are the issues going forward with this? So I think the theory is fine, right? The theory shows you how you can compute these likelihoods for any model, right? It's got to be a non-explosive Markov process with a countable number of demes. But of course, the prime practical consideration is what? It's getting the variance on the likelihoods low enough for it to be statistically useful. And that in turn, so that's the problem. But it's also quite clear what tools you have available to solve that problem. Namely, you have the choice of the importance sampling kernel. So you have a huge freedom to choose this thing. Essentially, almost no restrictions on it at all. The naive choice is always there, but it's not usually going to be a very good choice. So there are a couple of questions here. One is there an optimal choice? And I mean, I guess there must be an optimal choice in some sense, but exactly what that looks like is not obvious, right? Because we could come up with some very, very clever choice, but unless it basically the problem in importance sampling, right, is making sure that you sample the tails of the distribution adequately. And so that's going to be kind of tricky in terms of finding an optimal choice. That's what I want to say. So, however, we also have some observations that suggest that there may be some very nice ways of doing this. In particular, we can choose the kernel to borrow information from the future. In effect, in choosing the kernel, we can choose that to depend upon the data. It won't hurt anything to do that. The theory still remains valid. And so finding clever ways of doing that is probably the most important set of challenges that we face right at the moment. And we've got a number of different ideas for how to proceed in this direction. Happy to talk with other people about that if they're interested. So just to conclude, it turns out, and I didn't show this here, but it turns out that this theory, that as special case of this theory, all of the existing phylodynamic methods fall out. So the Kingman coalescent and the structured coalescence that have been derived from that are all special cases. You get exactly the same expressions if you make the same assumptions, but we can relax those assumptions quite a lot. This similarly with birth-death process-based methods that Tanya Stadler and her group have pioneered. Again, those fall out as special cases. This theory eliminates the need for any approximations that one might have to make. Now, there's very good reasons why those certain approximations might be good, and I'm not claiming that one wants to dispense with these methods altogether, but I think it's very useful to have a theory that gives you exact results. At the very least, it gives you a way of assessing how much impact the approximations one makes using simpler methods, how much impact those approximations have on conclusions. The computations that are involved, in principle, can be carried out completely forward in time. They don't have to be, but they can be carried out completely forward in time. And that liberates us to consider a much, much broader class of models, right? So the unfortunate fact is that almost all the models we're interested in can't be reversed in any meaningful sense. And so this is a great liberation. Similarly, the way that we handle sampling is completely opened up here. So any kind of sampling model we want to propose can be accommodated by this. I didn't talk about this, but if the basic technology we use to solve the filter equation involves sequential Monte Carlo, then assimilating other time series data at the same time that we're dealing with the genealogical data is a triviality. I'm convinced that there are probably some interesting applications outside of infectious disease epidemiology, but I have yet to really find a nice use case. I'd love to talk to people about that. And the full details of everything are to be found in this preprint here. So I'll stop now. Hopefully, we have time for a few questions, but I'll leave that to you, Eric.
Thank you very much. Yeah, that was very interesting. I wonder if you could talk a little bit more about like the state of play as far as software implementation, and like, let's say I want to try this out and play around with it. I know, does this sit inside POMP?
So the state of play is, I'd say we're not quite ready for prime time, in the sense that there are software implementations of these algorithms for certain models. In this package I've written called PhyloPomp, and that builds on top of POMP. So it uses, to solve the filtering equations, it uses POMP, but it basically constructs the simulators according to the equations I've shown here. So the key problem is that, given a model, one can, given a model, this filter equation is determined, right? This filter equation follows through a mechanical application of procedures, analytical procedures to produce this filter equation. given the model and the choice of important sampling kernels, this equation takes a specific form, right? That has, where these integrals become just a few sums, a few terms, right? This dramatically reduces in complexity to something specific to that model. So one problem we face is automating that thing, right? So that's a symbolic manipulation problem. The second problem is, as I mentioned, exactly what are good choices of the important sampling kernels. That's another open problem. So there, if you want to play with this, you're welcome to download Phylopomp. It's on GitHub, and it's I mean, it's not stable, but I don't think it's broken. It's solid. I haven't noticed any bugs in it, and I've tested it pretty thoroughly. But it's still, we're a fair ways away from a tool that we can apply. So what I've envisioned is actually a tool where, similar to Pomp, where a user could specify a model and have the inference procedures be automatically produced and then available for use. But we're still a little ways out from that. And it's not clear that we want to do that in R either. But we're exploring some possibilities there. So that's the state of play right now.
Interesting. I will mention that the mathematical community is all awash in this thing called Lean, and like AIs can reason using Lean. And
what is it?
Lean. It's a way you can formalize mathematical expressions, and there's like alpha proof, which is an AI way for developing proofs using Lean. And I don't know. I mean, there's a chip. Maybe Lean could figure out not your optimal kernels, but maybe it could figure out some of the simplifications of these, so that you don't have to solve this differential equation, like you said, that sometimes these pop out in closed form.
Well, okay. Well, I don't know. I'm not sure.
I don't either. But I'll just leave that there and move on to an actually good question from Tanya.
Yeah, I'd say it's possible to. I mean, AI continues to surprise us, and yet there's good reasons to understand that there's some limits on that. Anyway, Here's the question.
Yes, thanks. For which models did you overcome the practical challenges? Your slide 22, such that the models can be readily used for empirical parameter inference. For all the models listed on slide 23.
On slide 23. No, that's work for you, Tanya. Yeah, not all of these models that are listed on slide 23 are actually probably, some of those models were chosen with at least with a substantial concern for making them tractable using more elementary methods. So probably if we were liberated from the need, this theory liberates us from the need to make some of those assumptions. So some of these models probably are we wouldn't want to revisit, but others, of course, are well worth revisiting. But there's 24 hours in the day, and so but by all means, I mean, the theory is clear. It should be possible to do that.
And Tanya's probably a little too polite to ask this, but you say correct. Have you identified specific problems with some of these models?
Well, for example, in some models, I mean, some approaches, rely upon there being a finite state space or something, and so there are strong assumptions made about, individuals being born at the same time that another individual dies in order to keep the population size deterministically fixed, or assumptions being made about sampling necessarily resulting in perfect quarantine, which in any given case may be in any given data analysis might be a reasonable assumption worth looking at, but it's quite clear that the true reasons why those assumptions were typically made was because the mathematical method required it.
Okay.
And so if you're liberated from those kinds of what's the word? obtrusive demands by the mathematical method, then you wouldn't be looking at those models.
Okay, so I mean, it's not like, yeah, I think I see what you mean. So I guess the main technical work to be done now is this like identification of the kernels and perhaps borrowing from the future to like understand what an optimal.
Yeah, I think that's right. Well, I mean, there's also technical work in implementation, right? So I think you mentioned before some new developments in terms of artificial intelligence manipulation of things. I mean, some of the manipulations are essentially computer algebra, right? And so those, that is can be done. And then there are other issues that are less clear to do with the how one actually solves the filtering equations. I guess it's conceivable that there are some very clever solutions lurking out there for specific cases, but the general case is probably going to need to be dealt with using some kind of a Monte Carlo approach or other. In which case, yes, the key problem becomes working out how to specify those important sampling kernels.
And it looks like Tanya was asking actually just exactly the same question, so we'll consider that.
Well, I mean, I understand. I appreciate, Tanya, that you're asking very practical questions. I'd say the jury is out on many of these issues, right? It's what this theory represents is I think a quite general and powerful approach to solving a problem that we haven't been able to solve before, which is, namely, what does the likelihood function look like for a general phylodynamic model? But it's not even clear that the gains that you stand to have in any given instance, in any given data analysis, it's not even clear that you stand to gain more from the exact likelihood computation than you would pay for the computational effort to get it, right? It's nice to have an exact expression because if you care enough about a particular problem, you could at least in principle determine how much of a sacrifice you're making. But it's not even clear that that sacrifice is large, right? And so there are probably some cases, there's certainly some cases where the kinds of approximations that one has to make in order to make the simpler methods work are just not good approximations, right? If we have a small population size, we have very dense sampling, if we have strong nonlinearities, then all of those things are going to, or strong time dependence, we have variation in sampling effort, all of those kinds of things more or less directly go against assumptions that are needed in order to make the simpler methods work at all. It's one thing to say that there are approximations being made, but it's another thing to say that the errors introduced are large. So in any given instance, I don't know. I mean, they could be large, they could be small. All I've done is work out the mathematical theory. I think it shows the directions for that we need to go in order to answer the question that you ask about what the practical concerns are and where this thing will actually prove to be useful. But I think it's a mistake in general to think about this as just one more tool that we're throwing onto the pile of phylodynamic methods. That what I'm saying here in this first bullet point is that all of the other methods fall out as special cases of this, right? So this is a theory of phylodynamics, at least genealogy-based phylodynamics, that I think is quite general. It does leave the door open, and I think it's very, very worth going through that door to non-genealogy based phylodynamic methods, right? Where we don't even impose the tree-like structure, and those methods may prove to be both more tractable and more ultimately more valuable than these kinds of methods. But at least it's nice to have the theory clear for the methods that so many of us have been using.
Yeah, and I'm just curious to what extent there is a direct path. So, for instance, if we take the filter equation version of an MTBT, like a multi-type birth death process,
Mm-hmm.
do we directly those filter equations directly lead to the multi-type birth death process formalism, where you have like a probability that you observe a
That's a
lineage
really good question.
all, and then a probability of like the lineage up to time t, like
That's a
is
really good question. And yeah, so it's really interesting. So if you make the assumptions that if you basically impose, if you look at the Moran model, then and you solve the filter equations that correspond to that, you get exactly Kingman's coalescent, right? You get exactly the expression. But so far, and you can then do the same thing in the case of a linear multi-type birth-death process, single or multi-type birth-death process, and you can write down the filter equations. But I have yet, and you can solve them numerically and verify that you get exactly the same answer to any number of degrees of, to many degrees of, with a high degree of precision. But I've not yet figured out how to actually analytically derive those results. So that's still this kind of thorn in my side, this little pebble in my shoe, because I think it's got to be the case that those expressions fall out by solving this integral analytically. But I haven't yet been able to do it. And that's something that somebody who likes to solve thorny mathematical problem. I don't know how thorny it is. Maybe I'm just being dense, but potentially thorny mathematical problem, then I'd love to talk to him about it.
Yeah, that's cool. Yeah, I mean, definitely when I stare at that filter equation, it feels a little bit like that same like evolutionary probability.
Yeah, although in the linear birth death processes, the linearity assumption is exploited to it implies a certain self-similarity, which can then be used to make the equations right. So it's a little it's a bit different in terms of the way the argument proceeds. But as I say, there's got to be some deep connection there. Maybe it's more obvious to you.
No. I'm just like,
What's this?
just staring at it.
Yeah.
Well, that's awesome. I think we should probably wrap. We're well over time, but that was worthwhile. I hope the macroevolutionary community comes and says hello, because I mean, I don't know the open questions of macroevolution, and like I know that they've got thorny models. I know that they are limited in the expressivity of their models, but
yeah,
it would be cool.
I feel the same way. Yeah, I would love it if anybody who thinks about those kinds of problems wants to talk a little bit more, because like I was saying, I do feel like there's some possibilities there that this opens up, but I don't really know the field well enough to know for sure.
Cool. All right. Well, thanks again. And yeah, I feel like that was a great use of having like 2 talks to sort of like spread it out and make the mathematical expressions really clear. So thank you.
I'm glad. Thank you. Bye-bye.
Okay, bye.